How many digits? I've got a colleague of mine that works here who's in the older crew, and he at some point knew pi out 120 digits, and he can still recite it out 60. He can probably still do 120, I don't know. But that used to be like kind of like a pride thing, like, yeah, I know pi out 120 digits, how about you? But see, in the later generations, you don't really need that, right? Okay, so back to this. We're trying to do this by hand without a calculator. I have to do this. I know, because I come before the days of calculators, that root 2 is 1.414, okay? About. So try and do this by hand. That's not fun, is it? Okay, now try and do this by hand. What goes inside? 1.414. What goes outside? 2. That's easy. Right? 2 doesn't go into 1. Put a decimal. 2 goes into 14. 7 carried out 707. See how quick that was? See this? That's not going to be so quick. But you'll get the same answer. So the reason why we rationalized denominators back in the day was because it was easier to compute by hand. But for some reason, it has followed through this entire time, even when I was a student, where teachers still tell students, you must rationalize denominators. And there's absolutely no reason that it's necessary anymore.
And we do still get the same answer?
Oh, yeah. 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 Because, see, look, does 1.4 go into 1? No. Does 1.4 go into 10? Yes. How many times? Shit, I don't know. Well, it turns out that it's 7. It's 7, and 7 times this, and you put that here, and then the next thing you're going to get is like a 0, and then it's going to be a 7 again, and it will be exactly the same. It's just harder to do it this way, right? Do you see how much easier that was to do? All right. That's it. That's the reason.
But concerning the original problem, would
Yeah.
it be okay still if, like,
If you wanted to come in here and do...
if I, like, radicalize...
That, to me, would be admirable, but you're torturing yourself. We're at the answer here. There's no need to go any further. You're, I don't know. I'm not good at analogies, but you're working harder than you have to. And it's always better to work smart, not hard, right? All right, next one. I don't even think I need to look at it. I'll just make one up. Limit x approaches 5 of 1 over the square root of x plus 4 minus 1/3 over x minus 5. What is the form of this limit? 0 over 0. So it is 0 over 0. I'm not going to write it down, but this is bad. What I've done in this problem is I've actually combined 2 issues into one. Do you see it? We have a complex fraction and a radical. So what do you do first? Combine them together first. All right, so I'm going to get a common denominator. I'm going to put these 2 together. You ready for that? That means I'm multiplying top and bottom here by 3. And I'm multiplying top and bottom here by what? Root of x plus 4. Root of x plus 4. Does this feel like algebra on steroids a little bit? Does it feel that way?
To me, it seems like just the next step.
It's like, yeah, now we're putting it all together. Okay. The algebra in this class is going to continue to get just, increased, and that's why I said in the beginning, it's not the concepts, it's the algebra that gets the students. All right, well, next line, limit again. Okay. 3 minus root x plus 4 over, yeah, now be careful on here, it's 3 times root x plus 4, which is not the same as 3 minus. And then all of that over x minus 5. That looks pretty ugly, right?
So
Any questions on how I got that? You could verify right now, if you wanted to, you could verify that if you plug in 5, you're still going to get 0 over 0. It's still going to be undefined. And it's always going to be that way until you get what to cancel? This x minus 5 to cancel. And you're not even close yet. So what do you want to do now? Hit it with the conjugate. Hit it with the conjugate. Because you see a radical in there now, right? See how that radical is like an a minus b? See, over here we didn't have that, did we? This wasn't like a minus b. I mean, you could say it's a minus b, but notice the radical was on the bottom. So you had to kind of get the radical up top before you can do the conjugate. So I'm going to come in right here next to it, multiply by a 1, but the one I'm using is 3 plus root x plus 4, 3 plus root x plus 4 again. And boy, you have to be real careful with your signs here.
Why would you get rid of the x minus 5 first?
Get rid of this? How do you mean get rid of it?
1 over x minus 5. No. Yeah.
You mean like bring that here too? You could. What I'm doing is I'm doing kind of a more systematic way. I'm putting my fractions together, and then I'm going to do a conjugate. And once I figure all that out, I'll bring that thing up when it's time. All right, so here to here, right? The middle terms won't matter, and then the last ones. That's what it's going to be, right? So let's talk about the first one. 3 times 3? 9. All right, this is where I said you have to be real careful with the sign. The root here and the root here multiply together, and the root goes away. You're left with x plus 4. However, because this was negative and this was positive, it's subtraction. It's subtraction of that entire quantity. So it should look like this. Minus x plus 4. I'm putting in parentheses. I'm not going to distribute it through yet. All right? So it's negative, and then it's whatever was underneath in parentheses. That is over an ugly looking thing. It's this times this, right? Times these two terms. And I'm not going to try and multiply those out, okay? I'm waving my hands at that. I'm saying, look, I hope I'm never going to have to deal with that multiplication. I might, but that's what it is for now. It's just whatever that times that is. Then all of that over x minus 5. Do you have any questions? I'm hoping for something good to happen here. Remember, I want that x minus 5 to go away at some point. What is 9, and then if you distribute this, what's 9 minus x minus 4?
0.
X minus 1, x plus 5.
Here, let's do this. What's 9 minus x minus 4, right? If I distribute that through.
Negative x minus 5.
Negative x plus 5. 5 minus x. Right?
Right.
Okay. Limit. X goes to 5. This top is 5 minus x. The bottom is this big, ugly, nasty looking thing. Then all of that over this thing, right? Which I could write as 1 over 1. But I'm going to go ahead and bring that up now, if that's okay with you. I'm going to bring this and flip it up like this. That fine with you? Times 1 over x minus 5. We're close. We are close. We're only off by a sign, right? We're off by a sign. This is x minus 5. This is 5 minus x, so I'll need to factor a negative 1 out of the top. So let's do that. I'm just going to put a little line through that, and above it I'm going to write negative 1, negative 5 plus x. And then I can cancel these out.
Negative 1 over all that.
-1 what?
Overall.
Yeah, over all that. Man. Time flies when you're having fun, huh? Yeah, so this went away, and that still has a -1. Don't forget the -1 up there. Then all that junk, and good for me, I'm not going to have to deal with it. Like, I'm just going to be able to direct substitute now. Yeah, I've got -1 here. No longer need to write the limit. 3 times, when I plug 5 in here, I'm getting 9. Root 9 is 3. So I have 3 times 3. And then I have in parentheses 3 plus, and if I plug 5 in here, I get 9. Root 9 is 3 again, so 3 plus 3. And I could have given that to my 302 students, and they should be able to do that, right? -1 over, what is it, 54? All right, so that's a pretty heavy one there because there's a lot involved. You're going to need to practice, right? Going to need to practice. All right, we've got a little under 20 minutes, and I still have another concept that we need to discuss. I won't complete all of it, but I'll at least get us introduced to it, all right? Looks like you're in for a good weekend, huh? Yes, we're still in the same section. And I've never really liked how this book handles this section because, I don't know if we talked about this book, but not a huge fan of the book. I like the author, okay, but this book is called Essential Calculus, and it's a condensed version. The same author makes a book that's about twice as thick that covers the same material, and there's just a little more examples, kind of a walkthrough, like easy, medium, hard type problems in the exercises. This is more like, this is a great reference book. Like after you finish Cal 1, 2, and 3, like this is a good book to have on the shelf to go back and look at. I'm not real big fan of the way they handle some things in here, especially this topic right here. I've always liked to see this in its own section. Like this is its own topic, separated from everything else. But it's the way it is, okay? So here we go. There were 2 limits that you need to know. I'm going to put them right here. Limit x goes to 0 of sine x over x. The other one, limit as x goes to 0 of cosine x minus 1 over x. This one is equal to 1. This one is equal to 0. You need to know those. But I kind of teach this a little different than the way they appear here. I think the way I'm going to show it to you hopefully will allow you to do more complicated problems easier. So my slight adaptation to this is this. If you are ever looking at a limit, okay? If you have a limit, and let's say you have something here approaching something. Now I'm leaving these as boxes because they could be anything. It could say x is going to 1. It could say t is going to 0. It could say p is going to pi. It does not matter what this is, all right? So you're looking at a limit. And then up on the top you have sine, and inside of the sine you have something that I'm going to call junk, okay? You've got some junk sitting inside of the sine function. It might be x, like here. It might be x squared, might be 3x, might be x squared minus 1, might be cosine of x. It could be anything, all right? It's just some junk. And then below it, you have the same exact junk, right there. So do you see that that's what this is? Sine of some junk over some junk. Do you see that these two are the same? Yes? Good. The answer to this is equal to 1. Well, let me erase this if. I don't like the way that sounds. The limit of sine of some junk over some junk equals 1 if two things are true. First, junk equals junk. What I mean is that that junk equals that junk. They have to be identical. I already said that. It says junk and junk. I know it's kind of implied, but this is just to stress it. Those must be matching perfectly. If that's true, and the second thing, the junk, what? The junk goes to 0. The junk is approaching 0. So as you take this limit of whatever it is, this junk goes to 0 and this junk goes to 0. If those two things happen, then the answer is 1. Right? The answer is 1. Doesn't matter what it is. So you see this? These two match, right? Let x go to 0. Did that just go to 0? Did that just go to 0? The answer is 1. Now let me show you a couple of other illustrations of this. And I need to add one more thing before I do it. This formula also works if it's flipped over. If you have the junk on top and sine junk on the bottom, this will also equal 1 as long as those two conditions are met. So it does not matter. And if you want, I'll put the quotes on here if you need the quotes. There you go. You got the quotes. So if this problem would have said, if this right here said x over sine x, the answer would still be 1. All right. We are going to address this one next class. We'll get into this one. But for now, let's do a couple of problems like this. All right. Here's an example. What is the limit as x goes to 0 of sine of x over 4x? So does it fall into that pattern? Does this match this? No. But I can do something. What would be better if I had, instead of 4x down here, I had what? Just x, or it would be nice if I had a 4x inside, right? What's going to be easier, for me to have just an x down here, or for me to somehow force a 4x into a trig function? Just having a 4 down here is a lot easier. In fact, it would be almost impossible to push a 4 in there, because you can't. So instead, here's how I'll write this.
Sin x over x times 1.
Yep. That's the same problem, right?
Yep.
So it would be 1.
So we know now this goes to 1, doesn't it? This goes to 1. And so this is where one of those limit laws where I said if you're trying to take the limit of two things, you can do the limit on each one. What is the limit of a constant? The constant itself. What's the limit of this thing? It's 1. So the answer to this is 1/4 times 1, which is 1/4. Understand? Now I'm going to do a problem right next to it that looks a lot like it, but it's not the same. Ready? Limit x approaches 0, sine of 4x over x.
Pull the 4 out, right?
Can you pull the 4 out of the sine?
But you can add a 4.
You cannot pull things out of arguments of trig functions
But you can
because it's not multiplication.
But you can add a 4.
How do you mean?
You can multiply 4x.
I can just put a 4 here.
Or you can multiply by 1/4.
I can do 4 over 4. I'm allowed to do that, and that's exactly what I'm going to do. See, don't I want a 4 here? So I'm going to be really clever. It's kind of tricky. It's clever. I think clever is the better word. I'm going to multiply by 4 over 4 because that's 1. And sine 4x over x. And now because this is multiplication, I can put that 4 underneath here, right? and just really look at that as a 1 underneath. So my next line would look like this. 4 over 1 times sine of 4x over 4x. You see how I just like very cleverly, is that a word? Cleverly, okay, thank you. Cleverly inserted a 4 down here by putting a 4 over 4, sliding the 4 over. Now what does this go to? Take the limit of a constant, 4, and then times, this is 1 because you have junk, right? Identical. And as x goes to 0, this is important, as x goes to 0, 4 times x goes to 0. 4 times 0 would be 0. 4 times 0 would be 0. So our answer here is 4. Ready for another one? Of course you are. See it?
Oh, you can factor that.
All right, so this is where you just have to be careful because it's sine of something over something. These two do not match, do they? Now what happens as x goes to 2? That goes to what? 0. What does this go to? 0. So the two pieces are going to 0, but they're not identical. And you need them to be identical for that thing to work. So you would really prefer to have what down here instead of x squared minus 4? X minus 2. But it is there, right? If you just factor it. So I can turn this into sine of x minus 2 over x plus 2x minus 2. Like that. I could do that. And I can now see the piece I need, right? Sine junk over junk. I can see it there. But I'm going to split it up. And it's going to be sine of x minus 2 over the factor x minus 2 times 1 over x plus 2. Something like that. That's the same expression, right? This goes to what? 1 times 1/4. Answer is 1/4. All right. All right, I'm going to try one more. This is where the wheels came off for my other class, so let's see if the wheels come off here. Limit as x approaches 0 of sine of 5x over tangent of 3x. Yeah. All right, let's talk about this. When you have a limit, what's the first thing you're always supposed to do? Just direct substitution, see if you have a problem, right? Let x go to 0. 5 times 0, 0. Sine of 0, 0. So I'm getting 0 on top. On the bottom, 3 times 0 is 0. Tangent of 0 is 0. Now, if you need to go back and review your trig functions, you need to do that like ASAP. All right? You need to know sine, cosine, tangent at all the common angles. 0, pi over 6, pi over 4, pi over 2, pi over 3. Know all those trig functions, especially 0. All right, so we have a problem. There's no factoring we can do. There's no conjugate. There's nothing else that we can do to this. The only hope we have is, at this point, is the junk thing, the sine junk over junk. So here's what I'm going to do. See how far you can follow me. I'm going to first rewrite this. And I'm going to, what I call, peel it apart. I'm just going to start peeling this fraction apart. All right, so all I've done is rewritten it as two fractions instead of one. And then I remember that from pre-cal, 1 over tangent is really cotangent, right? And cotangent is, which one is it? What over what? Cosine over sine. So this is actually the same as the limit as x goes to 0 of sine of 5x over 1 times, you said it was cosine over, so this should be cosine of 3x over sine of 3x. That okay? If I do it that way? Now I'm peeling it all apart. Here's why. I would like to identify what the problem is. And for me, the problem is that sine 3x. This is what's creating division by 0, isn't it? That's causing division by 0. Look, if I do sine of, plug in 0, we get sine of 0, that's 0. 0 over 1, that's not a problem. 0 over 1 is 0. Cosine of 0 is 1. 1 over 1, no problem. 1 over sine of 0, 0, that's division by 0, that's an issue. This thing is what makes everything like go crazy, right? What would I love to have right here on top? What would I love to have had there instead of a 1?
Or a 3x.
A 3x. How about a 3x? Wouldn't a 3x just be great if I had a 3x there? I could put a 3x there. I'm allowed to do that as long as I do the same on top and bottom, right? So I'm about to introduce a 3x on my own. It's my own call here. I'm going to introduce a 3x on the top and the bottom. Got it? Top and bottom. Right here. But I'm going to slide that 3x that was on the top up there, which leaves me with a what out here? 1 over 3x. And so you're like, ha ha, I fixed it, right? We know this is good. We know this is good. We know that's now 1. I still have the problem, right? Because as x goes to 0, this is still bad. Isn't that bad?
Yes.
Okay, now I'm going to look for a weakness. I'm going to look for weakness in the problem. Is there a way that I can exploit what I see to resolve that 3x problem? It's really not the 3 that's causing the problem, right? It's actually the x that's causing the problem. You ready? Here it is. I'm going to take this x, just the x, and since this is all multiplication on the bottom, I can move it anywhere I want, right? I'm going to choose to slide it underneath this right here. Okay? I'm moving this x right there. And it's no longer here, is it? Agreed? Now, why did I do that? Because now I can say, all I'm missing here is a 5. And I can introduce a 5 on the top and the bottom. So here I go and I throw a 5 out here, a 5 on top, and a 5 on the bottom. But what am I going to do with that 5? Move it over there. So I'm really going to leave a 1 here, and I'm going to put a 5 here. And look it, I've made the problem disappear, haven't I? I've made the bad thing go away because I was able to take it and use it under this sine of 5x, create a 5x out of that x, as long as I put a 5 in here. A 5 over 5. And now at this point, if you look at the entire limit, everything is good. What does this go to? 1. What does this go to? 1. What does this go to? 1. What does this go to? 1/3. What does this go to? 5. So we have 1 times 1 times 1 times 1/3 times 5. The answer is 5/3. Okay, we'll need to see a couple more of those. All right? If you feel like what happened just now, that was the reaction of my other class also, like what's all that sliding things around, you know? But this to me is an important problem because it really is one of those first problems that you ever see in this class where it's not just a methodical little thing. You have to actually kind of come up with the way you're going to do it. Okay, we're going to call it a day. Your homework is to do the homework for 1.4. You are going to probably have some issues when you get to problems, the problems that are in the late 50s, I think like 53. Yeah, you're going to have problems with like 49 through 56, those problems, because those are all like this, like this. So if you get to those, you know, you can hold off. You don't have to do them. All right? I did a couple of them on the videos. I didn't do them all, though. I'm not going to take attendance. I'm going to base it upon the quiz you took today. So if you were here and you took the quiz and you turned it in, you will be counted as being here. All right? Any other questions? Yes?